So my project is titled Virtual Dance Therapy, AI-Driven Environments for Stress and Addiction Management. My name is Arya Devanath, and this work explores how rhythmic movement, especially Bharatanatyam-inspired part patterns, interact with physiological stress patterns and how AI can detect these changes. The background. So physiologically, stress affects the autonomic nervous system and shows up in measurements like EDA and heart rate variability. So addiction also disrupts reward pathways involving dopamine and prefrontal regulation. Research shows movement-based and rhythmic therapies can help stabilize emotional responses. So this forms the scientific basis for studying dance as a therapeutic tool. So Bharatanatyam and other rhythmic dance forms uses geometric and structural movements that naturally sync with breathing and internal rhythms. Because VRIR, they can deliver controlled movement environments. Combining rhythmic movement with real-time biosensing creates an opportunity to personalize therapy. So that specifically motivated me to explore whether AI can detect stress changes during movement. Introduction. In this study, I investigated whether physiological stress reduction during rhythmic movement could be measured using EDA and whether machine learning program models could predict those changes. I also used PCA and correlations to explore how movement-related features relate to physiological responses. So ultimately, the long-term goal is to support adaptive virtual dance therapy systems. So the key objectives were to first measure physiological stress reduction from rhythmic movement. 2, combine behavioral and physiological data for multimodal analysis. 3, develop AI models that can classify stress reduction states. 4, map rhythmic entrainment using machine learning. 5, build a foundation for VR and AR-based adaptive dance therapy. So results here, starting with raw versus processed EDA. So this figure shows the raw versus processed EDA. After cleaning, we get a much smoother signal that's easier to analyze. So this pre-processing removes noise and drift so the model can focus on true physiological stress responses. This is here, it explores how synthetic movement-derived features correlate with EDA-based stress levels. So the correlations are weak, which makes sense because rhythmic entrainment is nonlinear. So this is exactly why we need machine learning models instead of basic linear statistics. This is the PCA plot, which reduces all the features into 2 main components. We can see clusters, which are representing the higher arousal versus recovery. And this supports the idea that physiological states during dance sessions change in structured ways that AI can detect. This time series dataset, this shows a large initial sympathetic spike followed by a steady decline. So this matches what we expect from traditional habituation. Stress rises at first, and then the body stabilizes as rhythmic movement continues on. And then would be the random forest model here, which achieved a perfect classification. It could clearly distinguish stress reduction states from persistent states using the engineered EDA features. This demonstrates that rhythmic movement produces predictable autonomic patterns that AI can identify with high accuracy. So now I'll kind of walk you through how I conducted my research and how I extracted the EEG signals from a Bharatanatyam dance video using Python. So here, these are the files used in my analysis. So the MOV file here is the Bharatanatyam dance video that I personally performed specifically for this project. So to extract the brainwave information from the video, I used Python notebook called dance IPYNB. This code takes the dance video and converts it into an EEG-like signal format. So the extracted EEG data gets saved as a Laripu EEG signal.CSV. So Laripu is just the, and this represents the neural activity during my dance movements. So to test whether the AI model can correctly interpret stress levels, I also created 3 synthetic EEG signals. So we have high stress, low stress, and medium stress. So these stimulated the signals help us compare my real EEG-like data with controlled stress levels. So all the EEG signals, both the extracted dance signal and the synthetic ones, were analyzed using another notebook that we called EEG signal analysis.ipnynb. So this notebook calculates the patterns in the EEG, such as changes related to stress, arousal, or emotional activation. So I ran the code one by one for the extracted EEG and each synthetic EEG file. So the plot shows which signal has the lowest stress, which has the highest stress, and how my extracted data, dance EEG, compares. So finally, using the EEG signal, the AI model produces a recommendation. So for example, if this is, we going to combine the low stress, if we run it, it'll give you the synthetic EEG signal and then AI recommendation saying stress levels are low, maintain current dance intensity. It's saying focus on deep breathing during the sequence, different synthetic EEG, short pauses for medium. For high, it'll say increase slow rhythmic dance sequences, yoga, stresses, etc. in its recommendation. So, okay, we have this, and then more really within the real world, future system, instead of text, the AI will recommend the next dance step in real time. So in the real world version, a dancer would wear an EEG headband and a VR or AR headset, and as they dance, the EEG headband reads their stress level, and the AI automatically selects the next therapeutic movement, adjusting the rhythm, speed, or intensity. Overall, my research simulates how EEG could be, extracted and analyzed during dance movements, and how AI can use this data to make real-world therapeutic recommendations. My results show that the EDA pattern during rhythmic movement follow a nonlinear but consistent physiological trend. So nonlinear models like random forests and RNNs perform better, meaning the stress reduction process is complex and time-dependent. A major limitation is that I didn't have access to an EEG hardware, so I couldn't study deeper reward system changes related to addiction. Future work will require EEG, motion sensors, and heart rate variability for more complete analysis. And then in conclusion, this project provides strong evidence that AI can accurately detect stress reduction during rhythmic movement using only EDA signals. These findings support the development of adaptive VR and AR dance therapy platforms. So with EEG and motion tracking integrated in the future, we can expand this to addiction-related circuitry and create highly personalized therapeutic environments. And then these are the key references that guided the scientific foundation. And yeah, that's it. Thank you.